All right, taking a look at number 3 now for the 2015 exam. It says Johanna jogs along a straight path from 0 to 40. Her velocity is given by a differentiable function v. So it's differentiable, which means there's no like corners or breaks in the graph if we actually plotted this out. Selected values of VFT where T is measured in minutes and VFT is measured in meters per minute are given in the table. Use the data to estimate. So what I did here is I just took a couple of the pieces over because we're only going to do one part at a time anyway. So for part A, use the data to estimate the value of V prime at 16. All you have to do that is like the slope of the velocity. So you're going to do 16 is between these. So we're going to do the change in y over the change in x. Make sure you put the y's on top. So I'm just going to write that up here. We're going to do v of 20 minus v of 12 over 20 minus 12. You don't necessarily have to write that. I just find that's the way the key usually has it written. So I've got the 240 minus the 200. 20 minus 12 would give me the 8 there. So I end up with 40 over 8, which should be 5. If we had to label this, you want to make sure that you're careful with your labeling. Okay, your y's are in meters per minute and your x's are in minutes. So this would be meters per minute squared or meters per minute per minute. It does not say to label it, so we should be good to not label it here. And double checking our key just to make sure we didn't mess anything up here. They're telling me that part A is just the approximation, so 5 is the only thing you're going to get a point for there. Okay, so let's go ahead and jump into part B then. For part B, it says using correct units. So here, make sure that you're finding the units. Explain the meaning of the definite integral. So we're given the integral, it's got the absolute value on it. So when it's got the absolute value on it, it's going to make all those negatives positive, which is going to make your value a lot larger than what it would have been if you would have, actually calculated these negatives in its spot. So what that's going to do is it's going to give you the total distance traveled. So whenever you see the integral and the absolute value of velocity in it, that's the total distance traveled. And if you think of this as Riemann sums, which is what we're going to be doing here, we're talking about these rectangles. Across the bottom, we've got minutes. Up the side, we've got meters per minute. If you multiply meters per minute times minutes, you're just going to get meters. So that's going to be my using correct units part. So explain the meaning of this definite integral in the context of the problem. So it would tell you, I'm going to write it out here, the integral from 0 to 40, that's in minutes. So we'll make sure we address that. Sometimes I find people accidentally leave that off. It would be the total distance traveled in meters. Let's see here. So that's how the total distance traveled in meters, and that's how far she's jogging. So it's the total distance Johanna jogs in meters from time t equals 0 to t equals 40 minutes. Okay, so we've answered kind of the first line here of it. And then it says to actually approximate the value using a right Riemann sum with the 4 subintervals indicated in the table. So if you need a little sketch, and don't be afraid to, kind of do it off to the side here. They're not going to give you points for it, but doesn't mean you can't do it. So we're starting at 0, 0. And then we're going to 12 here. And the height is 200. And then we go to 20 here, and our height is 240, and then we get to a negative, which we'll deal with in a second. But the the main process here is taking the base times the height, and we're doing a right Riemann sum. Be real careful that you look at that. So going from here to here, our base is 12, and then our height is 200. And then our next one, our base is only 8. So I'm going to kind of start the process on the table here. So I went 12 and then 200. Then my next one is going to be here 8, and our height is 240. And typically here, what we're going to get here is our 4, and the next value be negative 220. But you have to realize here that it's an absolute value in this case. So we're approximating the absolute value. So that negative 220 is actually going to be a positive 220. And then from here to here, we've got our 16. And then the 150 would be that right Riemann sum. And it keeps me from accidentally like missing one, or I don't know, using the wrong side. Make sure you look at that. And I would circle that for my answer, honestly, but using my calculator, I can quickly get 7,600 meters. You don't want to waste your time typing things in your calculator when they're not going to earn you more points. So literally, I would leave this, and then I would just write meters behind it. But that should be our answer. I'm going to check the key here, and we'll see what we get some points for. So I already said for part A, it was just the approximation here. So we got that part right, the 5. For part B, explanation, so that would be this part up here. It looks like we got it. We wrote this a little bit differently. Another point for the right Riemann sum, which would be really writing out this part here, I suppose, and then the actual approximation of the 7,600. I don't know why those are separate. Actually, I probably do know why, because sometimes it'll say to find like what the average is. And if you're trying to find the average over that 40 minutes, you would have to take like 1 divided by 40 out front, and then have a parenthesis with all of this. And then a lot of times they'll give a point for what's in the parenthesis. They'll give a point for the Riemann sum part of it, and then they'll give a point for remembering to times it by the 1 over 40. In this case, there's not that extra step. Okay, now jumping to part C and D, I just left the intro stuff up there and got rid of A and B there. So part C says Bob is riding his bicycle along the same path. His velocity is modeled by this function, where t is the time in minutes and b of t is measured in meters per minute. So similar to this, only now we're given an equation. Find his acceleration at time 5. So if this is his velocity, then in order to get the acceleration, we need to take the derivative, which is pretty easy here. We got 3t squared minus 12t, and we want it at 5. So we want b prime of 5, which would be 3 times 25 minus 12 times 5, and you could circle that for your answer. I got 75 here minus 60, so 15. And if we needed a label for that, this is an acceleration. So this was in, hold up, here we go, meters per minute. So this would be in meters per minute squared. Not that we need a label there, but that would be our label. If I check the key here, it says uses b prime of t as a point, so we did that, and then the answer of 15 is your other point. So we got our 2 points there. Now for part D, D says based on the model B from part C, so we're still using this model, find his average velocity during the interval. So if we're trying to find the average value, so we're trying to, really that's what we're trying to find. We'd want to use the equation, the 1 over b minus a out front. This actually will not be tested in 2020, so you would not have to do anything like part D. I will just quickly show you how to do it. You do the 1 over b minus a, which was 0 and 10, so you do 1/10 out front, you do the integral from 0 to 10, and then you would just put the velocity function in here, which is b of t dt, and that should get you full points, but we do not actually need to do that here, just because this year they're cutting that content from the test. Okay, and because this was a no calculator chunk to the test, you won't have a no calculator chunk, but they still would expect you to be able to do antiderivatives and things like that. So what the student would have to do here is actually put this function in, do the antiderivative, and do their work through the end. The answer to this, it's a average velocity, so your label would be in meters per minute. It's always good to think about what the labels are for those problems.